Good day, everyone. Welcome to ME160 Damped Harmonic Excitation. So before we start, mag-review lang tayo ng ating tinahak nung last meeting. So, nag-examine tayo ng what we call harmonic excitation for an undamped system. So for this case, meron tayong non-homogeneous component ng ating equation of motion, that is the forcing function, which is equal to F naught cosine omega t. F naught is the forcing amplitude, omega is the forcing frequency. Now, yung total response ng ating system will be something like this. We have two parts, a part that resonates with the natural frequency of the system and a part that resonates with the forcing frequency from the disturbance. Ngayon, pinrioritize natin ang ating steady state response. We have two components. Una is what we call the steady state amplitude or just capital X. Itong capital X na to, we can look at a normalized value of this by dividing it by F naught over the stiffness K. So yung F naught over stiffness K, that is the induced deflection ng ating forcing amplitude. And when we divide that, when we use that to divide X, we get what we call the magnification M. Ngayon, may isa pang part, that is the forcing frequency omega. Si forcing frequency omega, we can normalize that by dividing it with the system's natural frequency. And when we graph these two together, we get this interesting graph. Ngayon, meron tayong four cases all in all sa graph na to. Pero ang pinaka-importante and yung pinaka-dangerous is that asymptote here. This asymptote indicates that our value for the magnification is almost infinite. So when the forcing frequency matches the natural frequency, we get what we call the resonance effect and our amplitude goes absolutely wild. Now, ganito pa rin ba yung case pag may damping tayo? Pero let's take a few steps back. Saan nga ba tayo nakakuha ng what we call the forcing function or harmonic excitation? So, in mechanical engineering, usually, they come out of two phenomena. So, first is a rotating unbalance. So, pwede manggaling to sa turbine, compressor, pump, or any other rotating device. Pag yung device mo ay hindi balanse at umikot siya, pwede siyang mag-induce ng harmonic excitation as you see in this animation. May instances din na you have air or water or some other fluid na nagfa-flow over your system, and because of the little disturbances caused by your system, nagkakaroon ng oscillation. So, fluid flow can induce harmonic excitation as well. Ngayon, ano yung mga pamprotekta natin? How do we guard against these kinds of excitations? So, una nating isipin is damping, of course. Pero ano bang mga bagay-bagay ang maganda sa damping? So, tandaan natin, lahat ng materials na ma-encounter natin sa tunay na buhay ay merong kaunting damping. Nagbabago lang yung damping na yun, yung level of damping na yun, depende sa property ng ating materials. So, dito sa kaliwa, may makita tayong plot. We call this the Ashby plot. It can be actually the x and y axis values here can be different. Pwede siya i-swap out. We use Ashby plots to determine which material is best for what application. For this case, meron tayong Young's modulus, GPA. So, it's comparing yung ating tensile saka tensile slash compressive na capability versus this loss coefficient. Yung loss coefficient, it's for very low damping ratios. Half of the damping ratio lang siya. So, you can think of the loss coefficient as parang same magnitude lang ng damping ratio. Makita natin dito na ang ating mga materials ay along a certain slope. On one end, we have our metals na nasa gray zone. And we have all sorts of other materials. Ngayon, yung mga metals, they have a strong Young's modulus, pero they have a very low loss coefficient or damping ratio. These materials are not great at being dampers. In fact, they're so bad that yung magnitude ng ating mga damping ratio slash loss coefficient ay 10 to the negative 3. That is 0.001-ish magnitude. That's very low. Particularly for steel, that's actually quite low. It's almost negligible. So may mga certain exemptions dito pero we usually don't see them in vibration control or vibration suppression. Ngayon, on the other end, meron tayong mga bagay na mababa, yung Young's modulus, pero matindi yung loss coefficient or damping ratio. These are foams or rubbers. Kaya kadalasan if you search for vibration absorber or vibration isolator, ang makikita mong mga bagay-bagay ay itong mga components na meron ng suotan ng mounting, itong mga butas na to sa gitna or mga butas na nakadistribute, and may part dito na rubber or silicone. So, yung mga materials na to, rubbers, foam, silicone, they are excellent in absorbing or dissipating vibration energy. That is why ito yung mga kadalasan na sineselect natin. So in essence, yung ating mga metal frames for structures and components, they do have a damping ratio inherent to them pero napakaliit. Like, sobrang liit. So another thing is that when we introduce damping to our system, ang nangyayari sa steady state contribution natin sa total response ay eventually nawawala. So makita natin dito sa graph, kulay black na to is the total response. Yung kulay green, yun yung steady state contribution, yung sumasayaw sa natural frequency ng system. Makita mo na eventually namamatay siya. And ang natitira na lang ay yung ating blue component which is the steady state component. Ngayon, we will be comparing yung ang effect ng damping sa location ng peak amplitude natin and dun sa value ng peak amplitude natin. So, pag walang damping, zeta equals 0, yung ating peak amplitude, I forgot to mention, ang nagbago sa y-axis natin is that in absolute value natin, yung magnification. So, etong part na to na nasa ilalim dati, pumunta lang sa taas kasi absolute value na. So, for undamped systems, ang ating peak amplitude ay nasa resonance or R equals 1 at yung value niya ay infinity. Ano kaya mangyayari pag naglagay tayo ng damping? So, yun yung kailangan natin bantayan for this session. So, first and foremost, um, konting derivation lang. So, this will be our equation of motion now. So, may damping term tayo ulit. That damping is C, the damping coefficient, times the velocity of our system. So, meron tayong steady state contribution or rather system contribution na sumasayo sa omega n. Pero as we've seen before, itong part ay nawawala na eventually. So, ang largest concern natin will be the steady state response. So, to do this, pwede tayo mag-MVP or MUC. Pero for this case, we use MUC. Now, in your module, chapter 5, the detail of this derivation is more clearly seen, pero napakahaba niya. If you extract or if you substitute this MUC and obtain the proper equations, meron kang terms that dance to cosine omega t. Meron ka ring terms that dance to sine omega t. If you group these terms into cosine omega t and sine omega t, you can split the equation into two. So you get a system of linear equations like so. So once you get there, we are able to get expressions for x cosine phi and x sine phi. Now, to get x, kailangan lang natin i-add yung squares ng x cosine phi and x sine phi and then square root them afterwards. Now, that process is left up to you to confirm. Pero, yung formula ng ating steady state amplitude x under damping will be something like this. And yung phase angle natin for our steady state response is now this. So, itong formulas na to, these are in terms of the system properties and the excitation properties. We can actually re-express these or transform them into forms that use the damping ratio zeta and the frequency ratio r. So, ang majorly affected nito is si x kasi when you re-express this in terms of zeta and the frequency ratio r, kailangan mo siya i-normalize. So, we will use the same technique of normalization for x and we will also normalize the phase angle phi. Buti na lang si phi hindi siya magbabago ng anyo. Si x kasi magiging m which is a dimensionless value. Pero si phi kasi angle terms are already dimensionless. So, once you normalize this, phi pa rin yung lalabas. So, after normalization from steady state amplitude x, we get our magnification. Yan yung normalized x natin in terms of zeta and r. And yung phi natin will be something like this. So, what I want you to notice is that if nawala si damping ratio, like you have an undamped system, etong second term na to ay mawawala and magre-revert ka dun sa luma mong magnification equation. So, sino ang mas okay tandaan? It's the damped expression for magnification. Ngayon, let's explore yung effect ng damping or for this case, para mas simple, let's explore the effect of damping ratio on our magnification plot. So, one way to think about the magnification plot is para siyang analog or parang representation of what the amplitude plot could be for every forcing frequency. So, when you see the graph, yung vertical axis niya is kind of um, analogous to the intensity of its vibration. So, ito yung itsura ng undamped system natin. What happens if we now activate our damping ratio? So, activating damping ratio. Whoa, okay. So, once we turn up the damping, what you see happens is that yung peak mo, it's no longer finite. Tapos, may hita natin na as we increase the damping ratio, paliit ng paliit yung peak value ng ating steady state amplitude. Another thing na ma-notice natin is that yung peak natin umuusog pakaliwa. And etong peak na to ay, or itong behavior na to at least, yung pakaliwang peak ay naglalast lang up to zeta equals 1 over square root of 2 or 0.7, 0.70, etc. etc. So, sir, bakit etong specific value? We will find out later kung bakit. Pero yes, that's what happens. Okay, paano naman kung nilagpasan natin si zeta equals 1 over square root of 2? What will the graph look like? It looks like this. So, essentially, after you've exceeded the damping of 0.707, etc., you no longer have a discernible peak. Hindi mo matatawag na peak yung r equals 0 kasi you have no frequency there. So, essentially, from that point on, yung amplitude mo ay bumababa as you increase the forcing frequency. So, yan. Okay. So, that's what we picked up. Pag meron kang damping, pag lumalakas yung damping mo, lumiliit ng lumiliit yung peak value mo. Until, essentially, wala ka ng peak value. At habang hindi ka lumalagpas ng zeta equals 1 over square root of 2, ang peak mo ay umuusog pakaliwa. Ngayon, can we quantify yung pag-usog nung peak natin pakaliwa? Yes, we can actually. Here's the plot indicating the movement of our peak. Pero before that, let's examine kung ano yung magnification natin at resonance, R equals 1. So, hindi na siya infinity. When you have damping, it's essentially 1 over 2 zeta. Galing lang to sa general equation natin. You can derive this easily. So, at resonance, your magnification is now 1 over 2 zeta. Pero ito ba yung peak? Of course, as we can see, hindi siya yung peak for every case. Pag all metal yung inyong vibration system, your zeta is around 0.001. Halos wala. Halos wala kang damping essentially. If it's all metal, it will behave almost similarly to zeta equals 0. So, yun yung difference with regards to undamped and damped excitation. Ngayon, paano nga natin kukunin yung peak value natin at paano natin malalaman kung ano yung peak value ng magnification natin? So, yung una natin kailangan hanapin is aling frequency ratio yung magkokos nung peak value natin ng M. So, to do that, we have to do some calculus or rather partial differentiation. So, we have to find the derivative of the magnification with respect to the frequency ratio and equate it to 0. So, of course, lalabas dun yung location nung peak value natin. Sir, kailangan ba namin siya derive? That is, the full derivation is in the module na. You can check that out. Pero yung final equation mo would be something like this. So, yes, this is the frequency ratio associated with the peak magnification. Sir, paano natin kukunin yung peak magnification? So, of course, i-substitute natin yung expression natin na bagong frequency ratio or back to the equation for magnification. And if we do that, we get the peak value of the magnitude, which is this. So, the R sub M sub max is the frequency ratio to cause the peak magnification, and M max is the peak magnification. So, mapapansin natin magkaiba sila with magnification at resonance. They're different. So, para mas madaling isipin, let's graph these with respect to the damping ratio. So, here are two equations. They're functions of the damping ratio. Let's graph the peak magnification first. So, of course, habang pataas ng pataas yung damping ratio mo, paliit ng paliit yung inyong peak magnification. And in terms of the frequency ratio to cause the peak magnification, makikita natin na pakaliwa ng pakaliwa or palit ng paliit yung frequency ratio to cause the peak magnification. And you'll see here that yung equation natin, dahil naka-square root siya, sa quadrant 1 lang siya nag-exist. Quote unquote. Walang sense kasi ang negative na frequency ratio. So our formula here for Rm max actually terminates at zeta of 1 over square root of 2. So you can prove that by equating Rm max to 0. So if you equate Rm max to 0, you'll get the value for the termination of the peaks essentially. So once you reach zeta equals 1 over square root of 2, essentially wala ka ng peak. Like, or rather, the peak doesn't matter anymore. So yeah, problem-solving methods for damped harmonic excitation. So kadalasan, when we encounter harmonic excitation problems, the flow of our solution can be one in two ways. Pwede na meron kang system properties, meron kang excitation properties, and kailangan mo palabasin yung steady state response. Pwede ganun. Pwede rin pabaliktad. Meron kang steady state response properties like X, M, or R, tapos kailangan mo palitawin yung system properties or maybe yung excitation properties din. So it's either of that direction. So let's look at one problem wherein we encounter wherein or rather we have system properties given to us and forcing properties. And kailangan natin palabasin yung steady state properties. So this example 5.4 in your module, you can view the full solution there in its appropriate location. Pero let's read this first. So we have a mass damper spring system with given mass damping coefficient and stiffness. It's being excited by a reversing force of 15 newtons with an adjustable frequency. So that means yung omega natin ay pwedeng bago-baguhin. So here, find the excitation frequency for which, number one, the steady state amplitude is maximum, and number two, the steady state amplitude is 10% of the maximum. So, alright, let's start with the given first. So, ito yung mga binigay sa atin. Ang pinapahanap sa atin ay find the excitation frequency omega for peak amplitude and 10% peak amplitude. So, magkaibang omegas to. Alright. So, before then, let's identify yung mga kailangan natin na equations. So, ito yung magnification and yung mga peak magnification relationships. So, makikita natin na critical, una is si R, saka si zeta. Do we have a formula for zeta? Yes, we do. And it just so happens na lahat ng items or lahat ng variables na kailangan natin for the damping ratio ay binigay na. It's C over 2 square root of mk. If you calculate that, you get this damping ratio. So, this damping ratio, check muna natin. Magkaka-peak magnification ba tayo or wala? So, kasi pag wala tayong peak magnification, essentially, the problem is moot. Like, wala siyang kwenta. So, buti na lang if we evaluate this against 1 over square root of 2, it is less than 1 over square root of 2. So, meron tayong peak value. So, yung omega max or yung forcing frequency to trigger the peak amplitude, we can get that by obtaining CRM max. So, we just simply plug in everything. Tapos, yung frequency ratio natin, it's the forcing frequency over the natural. So, to get the forcing frequency, just multiply Rm max to the natural frequency. So, natural frequency natin, it's square root of k over m. And yung Rm max natin is given by that formula. So, we will get the frequency. Yeah, we will get this frequency. So, it's kind of small actually. So, usually yung mga frequencies that trigger the peak amplitudes of systems usually malapit siya kasi sa natural. So, it's kind of small usually. So, now, to get the peak magnification, we just plug in the equation. So, M max. Sir, ba't natin kinuha yung M max? Kailangan lang naman natin yung frequency omega. That's because kailangan natin yung frequency omega for 10% peak amplitude. 10% peak amplitude. So that means kailangan natin yung value ni M max. So this is M max. Tapos yung kailangan natin na M for the second item will be 10% of this value. So that's M2. Ngayon, hindi na siya peak value kasi it's 10% of the peak nga eh. So we'll have to resort to the general M equation. So magkakaroon tayo ng quadratic formula. Ngayon, we have a quadratic formula. You can try shift solve if powerful enough yung calculator mo. Pero I would advise rearranging the equation into a quadratic formula first para mas madali. You can switch the equation mode of your calculator to solve this, or you can just straight up shift solve. Mag-iingat lang kayo dun sa lalabas na value ng R. Kasi it's possible na may dalawa kang positive values of R, may isa dun na mali. So if you examine, ayun nga, buti na lang, yung mga frequency ratios natin na lumabas, may isang negative. So immediately, that's dropped. So yung tamang value ng ating frequency ratio for 10% peak amplitude is R equals 2.9765 or omega equals 198 rads per second. So if you graph that, you get this. So ito yung M over R natin sa taas. And ito naman yung time domain response natin. So this blue, ito yung pangalawa na item. 10% of the amplitude. Yung green, yan yung at peak amplitude natin. Itong red, sa MR plot natin, this is the peak magnitude, peak amplitude, and this is 10% of the peak amplitude. So, ito yung itsura na equation na makukuha natin if we try to obtain a quadratic formula. So, from here, we have to rearrange such that we get this form. AR raised to 4 plus B R squared plus C equals 0. So, medyo may konting transposition pero okay pa. The next item will be actually a little harder. Sandali lang po. So, yun, hello, welcome back. So, this example 5.5 sa module natin. Here, we have a 30 kilogram industrial component na naka-install on an elastic foundation. So, can be anything. Can be springs with dampers, can be just a simple concrete floor. So, using a 25 Newton amplitude, nag-conduct tayo ng frequency sweep. So, in-adjust natin si forcing frequency omega. It was found that the system encountered its greatest steady-state amplitude of 1.5 millimeters when the period of the forcing frequency was around 0.25 seconds. Find the effective stiffness and the damping ratio of the foundation. So, ano yung mga given natin in this case? So, let's have a look. So, ito yung given natin. We have the mass, we have the forcing amplitude, but we have the steady state amplitude at max, and we have the forcing period at max. So, ngayon baliktad. We are given steady state properties and we have to find some missing system characteristics. So, for here, find K, find zeta. Let's pull up our necessary equations first para hindi nakakalito. So, anong kailangan natin for this case? So, lahat ng steady state properties na binigay sa atin, they are all set at the peak magnitude. So, peak magnification. So, yung mga equations na kailangan natin muna at the start would be yung mga Mmax equations natin. So, before then, let's adjust yung forcing frequency natin. So, meron tayong forcing period, madali lang naman i-convert. So, our forcing frequency for peak amplitude, is 8 pi rads per second. So, we know that M is the ratio of steady state X over the static deflection. So, ito siya, di ba? So, ngayon, we can get K if we just rearrange this formula. So, saan nanggaling po to, sir? Ito po yung original definition ng ating magnitude. or magnification M. So it's steady state amplitude X over the static deflection na caused by our forcing amplitude. So by rearranging this formula, we have a straightforward shot at the value of K. However, nawawala si zeta. Ngayon, there is an alternative. We can also get K from the frequency ratio R para mas madali. So yes, ang cool no? So we have two equations here actually. We have two equations. So two equations, ano lang susunod natin gagawin? So the next thing that we can do is actually equate this expression for the stiffness to this expression of the stiffness. Oh, magic. So, tingnan natin kung ano yung lalabas. So, ang F naught, alam natin. Ang XI, alam natin. Ang M, alam natin. Si omega to trigger the peak amplitude is kakasod lang natin, 8 pi. So, ang nawawala na lang is si zeta. So, ito, if you equate these two equations, medyo, masinsinan na pag-transpose ng mga variables. So, at this point, mag-iingat kayo sa pag-transpose. Be mindful kung ano nangyayari sa denominators ng either side. Para mas mabilis yung shift solve nyo, I suggest just moving the denominators or just multiplying the denominators of either side to the opposite side para lang mawala yung unknown variable sa denominator because that can cause your shift solve function to slow down. So, ang makukuha niyong zeta dito is actually, let me check. Okay, sorry about that. So, ito na. Yun nga, balik tayo dito sa ating problem. So, stiffness, may dalawa tayong equation for stiffness K. Equate them together and solve for zeta. So, everything else sa equation na to ay alam na natin. Pero para mas madali, let's clump all the known parameters together and let's equate them to A equals F naught over 2x m omega squared para mas madali mag-manage ng equation. So, if you rearrange this, una mong mapupuntahan is this equation. So, if ito yung mapuntahan mo, you can try to shift solve it. Ang warning ko lang is dahil naka-raise to yung highest order mo of zeta is to the 4, magkakaroon ka ng possibility of 4 possible solutions. Mas mainam na i-try mo siya i-group such that magkakaroon ka ng quadratic equation. Para you have the option of using equation mode. Equation mode using the quadratic equation, quadratic format. So, ayun na. Naka-arrange na tayo into a quadratic format para sa ating formula. And if you do so, magkakaroon ka ng dalawang roots. Tandaan natin yung roots natin will be z squared. So, isi-square root pa natin siya to get the actual zetas. So, oh no. Meron tayong two positive damping ratios. Sino yung pipiliin natin? So, it might seem hard, pero we just have to realize that there is a threshold for having peak magnification. And that is if your zeta is less than 1 over square root of 2 or 0.707. Which of these values is less than 0.707? Of course, it's this one, zeta 2. Zeta 1 is a valid equation, pero it will not cause any peak values or any discernible peak at all. So if you do that, our zeta then is this. It's 0.35, etc. So if you plug this into any of the equations for K, you also get your stiffness K, which is this value. So, ang itsura ng ating plot, it's this. So, yun, nasa peak tayo ng ating amplitude. Tapos, makita natin yung time response natin is also at the peak. So, medyo malaki-laki. So, yung mga problems natin sa damped harmonic excitation will probably be like this. It's either of these two. Galing ka sa system, given ka ng system properties, you get the response. Or meron kang piece of the response, piece of the system properties, solve mo yung mga nawawala na system properties. So, ngayon, napansin natin, in-ignore natin yung phase angle actually. So, let's look at the phase angle now. So, we have two equations. We have one using system properties and another using characteristic or normalized properties. So, sa undamped systems, if you recall, meron tayong case 1 and case 2. Sa case 1, si steady state response is in phase with the forcing function. That means yung phase angle mo is 0. Ngayon, pagdating mo ng case 2 or r equals greater than 1, ang inyong mga ang inyong steady state response ay 180 degrees out of phase sa inyong forcing function. So, yung phi mo is 180 degrees. Paano ngayon pag may damping ka na? Oh, okay. So, pag nagkaroon ka na ng damping, magkakaroon ng konting nuance, magkakaroon ng mga in-betweens sa inyong phase angle. So, for case 1, if yung inyong frequency ratio is from 0 to 1, then yung steady state response mo will be lagging sa f of t. So, parang nahuhuli siya ng konti. Pagdating mo naman sa case 2 region, which is frequency ratios of 1 and above, or rather above 1, yung steady state response mo ay mauuna sa forcing function mo. And for case 3, pag exactly 1 yung inyong frequency ratio, then your phi will always be 90 degrees regardless of damping. What you'd also notice is that pag tinataasan mo yung damping, mas nagiging patag yung curve. So, from zeta equals 0 na abrupt square wave or abrupt transient na response, pag nilagay mo ng konting damping, medyo magkaka-curve. Then habang pataas ng pataas, eventually nagiging parang pa-L. Naka nakayukong L essentially. Mas nagiging yukong L siya as you increase the damping. So yeah, that's what happens. For case 1 instances, ito yung itsura ng ating steady state response versus the forcing function. Forcing function is orange, steady state response is green. So, yung green function natin, habang mababa pa yung zeta, nakikita nyo, parang nahuhuli siya. Nauuna yung forcing function kay steady state response. And that lead kind of exaggerates as you increase yung zeta. Ngayon, for case 2 or r equals 1.5, medyo mahirap na i-discern kasi magkaiba na yung amplitudes ng steady state response o ng forcing amplitude. Pero in general, nauuna si steady state response kaysa kay forcing function. So it starts to lead. Medyo mahirap siya i-discern from this graph. Pero yeah, that's what happens. Ngayon, let's examine the total response. So, right now, in-ignore natin yung system contribution, yung mga omega n terms. Kasi nga, namamatay siya eventually, like nawawala. So, it only matters kapag in-start up mo yung machine. So, may sort of vibrations at the start, but eventually, it kind of goes away. Pero what if kailangan natin sila? What if kailangan natin yung system contribution sa total response? So, often our interest is in the steady state response X. Ngayon, we will only examine one case, which is the underdamped case. If we try the other cases, hahaba pa tayo, like tatagal tayo. So, ang magiging form ng total response natin will be something like this. So, to distinguish the system contribution from the steady state response, yung X at phi na associated kay system contribution will have a subscript not or zero. So, system contribution X not, steady state response is X. Steady state or system contribution is phi not, steady state is phi. So, after some solving, hindi ko napapakita kasi napakahaba. You can check the module for the full disaster. But after some solving, you'll get this expression for X naught and this expression for phi naught. It is horrendously large. Imagine mo na lang kung overdamped yung response natin. Medyo mas lalaki pa dito. So, if ever, just in case na magbibigay ako ng ganito, it will most likely be just getting the plain response. Like, mahirap na if you try to go from this system response to the system properties. It's kind of hard. So, just to give an example, ano itsura ng case 1, total response? So, tandaan natin, ang case 1 is frequency ratio 0 to less than 1. So, meron kang, yung steady state response mo is the larger wave, the gentler wave, I mean. So, yung system contribution mo, it kind of dies down eventually, giving way to your steady state response. This is also the case for peak magnitude. So, peak magnitude usually happens at case 1. So, meron kang steady state portion, pero yung meron kang system contribution pala, I mean, pero it all eventually dies. Just so happens na mas intense yung steady state response or steady state part of your response. For case 2, mas malaki na yung omega, yung forcing frequency. So, yung itsura ng steady state response mo would be very small and you can actually see it die down effectively. So, yes. So, for every time, for every instance, the steady state response remains. So, meron tayong example sa module, it's 5, 6. These are the given and we're asked to find the total response. So, dahil underdamped na in-examine natin, underdamped lang din yung example natin. So, here's the total equation. One tactic is to just state the equation and then solve for the missing variables or properties. So, like for example, if nasa prob set or nasa exam, you can just write down which equation is applicable to this problem and then just tag in all the unknown properties like zeta, x naught, and then just box them all together. That actually avoids errors sa final solution, especially for this case kasi ang dami mong kailangan i-solve. It's very dizzying. So, if we proceed, apparently sinolve ko dito is zeta first. So yeah, there's no harm in that. Pero usually ang sinasolve mo muna is omega n. So yeah, zeta and omega n. And from here, you can solve for the rest. So you can solve for the damped frequency and you can also solve for the steady state amplitude x in this case. Phi as well. Kaya mo na siya i-solve. Recall for our rules in phi and phi naught. We will, dahil ang calculator natin limited to single input arctangent, please be wary of the components. Please keep track of the components, I mean. At least yung sign nila. Si X naught, napakahaba na. I will not show the substitution, the process. It's basically this. Okay. And your phi naught is basically that. Now, if you graph this, your black is the total response, green is the system contribution, and blue is the steady state. This is the same graph that I showed you at the start. And that's it. So if you have any questions, kindly drop it at the LMS post, not the YouTube comments. Without further ado, thank you very much.